Effect of magnetic field on atomic orbitals. Electrons not only spin, they also revolve around the nucleus. So let us assume the orbit is a circle of radius r with the electron of charge minus e revolve around the nucleus of charge plus e in the z direction. We know moving charge produce current, so current I equal to q by t. Here q is the charge and t is the time. The charge is minus e and t is the time taken to complete one revolution. So that is 2 pi by omega. Omega equal to v by r. Here v is the linear velocity and r is the radius of the circle. So substitute the value of omega here. So 2 pi r by v. So substitute this value in I. So we get I equal to minus EV by 2 pi r. Here the revolution of an electron around an axis through another object such as the nucleus gives rise to orbital magnetic moment. Here orbital magnetic moment means it is the strength of a magnetic field produced by the orbital angular momentum of the field. So the magnetic momentum can be written as m equal to INA. So m equal to INA. Here I is the current, n is the number of rotation and a is the area. Here area is pi r square, number of rotation is 1 and current I we know minus EV by 2 pi r into number of rotation 1 into pi r square. So we get minus 1 by 2 EVR. In vector notation we write minus 1 by 2 EVR which is in the z direction, so z cap. So this magnetic dipole moment will have a torque when the atom is placed in a magnetic field. So the electron speeds up or slows down depending on the rotation of the magnetic field. Here during the rotation, the Coulomb force and the centripetal force are balanced each other. So the Coulomb force is balanced by the centripetal force. Here the Coulomb force is F equal to Q1 Q2 by 4 pi epsilon 0 r square and centripetal force is mv square r bar. So we equate these two equations. We write 1 by 4 pi epsilon 0, that is charge is Q1 Q2. So we write E square, two charges E square by r square equal to mv v square by r. So in the presence of a magnetic field, there is an additional force that is minus E V cross B. So let us assume that B is perpendicular to the plane of the orbit, which is shown in the or explained in the figure. It is so it is perpendicular to the plane of the orbit. So we write minus 1 by epsilon 4 by epsilon 0 E square by r square, the additional force plus E V bar B equal to me V square by r. Here we write E V bar B because the magnetic force is perpendicular to the velocity. So the velocity changes in direction but the magnitude is not changed. So the result is uniform circular motion. So the V cross B becomes VB. So combine this equation with this equation. When we equate these two equations, we get mv v square by r plus e v bar b equal to me v bar square by r. Here the v bar is the new speed. So after the introduction of b, the speed is v bar. Okay, so me v square by r plus e v bar b equal to mv v bar square by r. So we can write, we can take me by r outside, so v bar square minus v square. So it is in the form of a square minus b square. We can write as a plus b into a minus b. Here we assume the change, that is v bar minus v, that is delta v, is very small. Since the difference between v bar and v, that is the old speed and new speed, is very small, we can assume that they are nearly equal. So it can be written as 2v bar into del v. So v bar can cancel, me by r delta v into. So del v equal to ERB by 2me. So when B is turned on, the electrons speed up. So a change in orbital speed means a change in dipole moment. Automatically the dipole moment also change. So delta m equal to minus 1 by 2 E delta v into r z. So substitute the value of delta V, we get minus E square R square by 4m into B. So the notice that here the change in m is opposite to the direction of